All right. Hello, hello, hello. Welcome, folks, to the very first part of Unit 8. Probably our last unit. Not going to promise that, but most likely the last unit for the school year. We are going to be going through and talking about forces, and the first topic in this unit is going to be Newton's laws. Now, you are probably pretty familiar with 3 of Newton's laws, or at the very least, you should be familiar with the first one, and you've probably heard of the third one. Second one is an equation, so you might not know that one. The fourth one, most people haven't heard of before they get to physical science, so I'm guessing it's going to be new material. But we're going to start with the first one. So Newton's first law is called the law of inertia. An object in motion will tend to remain in motion. Object at rest will tend to stay at rest. Okay, and I just realized I forgot my tennis ball, so I will be right back. Okay, so what this law is basically saying. Oh, and an object at rest will tend to stay at rest. I don't remember to say that. So what this law is basically saying is that once something starts moving, it will not stop. Whatever velocity something has, it's going to maintain that velocity forever unless something causes that velocity to change. Okay, we call something that causes velocity to change or change velocity, that's acceleration. Something that causes an acceleration is called a force. Okay, that is a general definition of a force, is something that causes an acceleration. Okay, so if I put this tennis ball here and let it go, it should stay there, according to Newton's first law. It didn't, and I missed it, so now it's rolling across the floor. Okay, so it didn't stay there. Why not? Well, that means there had to be some force acting on it. Well, what force was that? Well, it's obviously gravity. Gravity is acting on the tennis ball, causing it to fall. It's inducing an acceleration, causing the ball to accelerate down towards the center of the Earth. Okay? So I'm going to go get the tennis ball, and then I'll pick up from there. Okay, I also added the definition of a force up here, so those of you who got a hard copy of the notes in class, that's not on there, you're going to have to add it. But that's, in a nutshell, that's Newton's first law. Okay, anytime something accelerates, some kind of force is causing that acceleration. Okay, that's why we did kinematics first. So you should now know what acceleration is, so understanding what force is should make a little more sense. Okay, generally we define a force as a push or a pull, but it's really just anything that causes an acceleration. Now, some forces are pushes, some forces are pulls, yes, but that is a discussion for 8.2, so we'll leave that there. That brings us to Newton's second law. Now, Newton's second law, there's no real good nickname for it. Newton's first law is the law of inertia. Everybody knows that Newton's first law is the law of inertia. Newton's second law, I've seen a lot of people try to coin a nickname for this one, and it just doesn't work. Newton's second law is an equation. It's F equals ma. Or more accurately, the sum of F's equals ma, which we abbreviate sum with a sigma. Yes, enjoy that, whatever. Okay, so sigma F equals ma, where the sum of forces is equal to the mass of an object times the acceleration that that object experiences. Okay, which is what this says. The sum of the masses, I can't read backwards. Hey, sum of masses acting on an object is inversely proportional to the acceleration the object experiences. Or, hang on, that's wrong. All right, so another thing you need to fix if you've got the handout, apologies. The sum of forces acting on an object is directly proportional to the acceleration the object experiences, okay, where m is the mass of the object. So the heavier something, well, I'm not going to talk about mass yet. Okay, so the harder you push, the faster the ball is going to speed up. The harder you throw the ball, the faster it's going to go. Okay, that's what we're saying. Okay, the larger F is, the greater A is. Okay, now we talked about mass versus weight a little bit in a previous unit, but I want to touch back on it a little bit. We're also going to distinguish between mass and matter for the first time because we've been saying They're synonyms. They're very similar. There is a difference. Okay, so mass is a measure of the amount of matter something is made of. Weight, which is force, is the force that gravity exerts on a mass. And matter is the sum of the molecules an object is made of. Now, there is very little difference between this first and third one, but there is a subtle difference. And at this point, you should know enough about what's going on to understand the nuance of that difference. So here are 3 more terms. That brings us up to 5 vocab words so far. We will not be doing anything with this equation in this class. However, there is an entire chapter in physics dedicated exclusively to this equation. So, if you take physics, we're going to do a lot with this. But if you're not taking physics, you won't have to worry about that. We're not going to do anything with that equation in here. All right, Newton's third law. Again, there's people have been kind of trying to coin a term with this one, coin a nickname. I've heard it called the action-reaction law more often lately, so maybe that one will stick. I have my doubts, but Newton's third law is the one that most people have heard of, and they usually know this definition, the one that's crossed out here. For every force, there is an equal but opposite reaction force. And while that is true, it is not a very good explanation of what the law actually says. That's a really good elementary definition. And honestly, this definition I have here is kind of more a college definition. So I'm going to try to paraphrase these two in a bit. But first, I want to read the second one here. Okay, the force that object A exerts on object B. So let's say the Earth is object A and object B is the tennis ball. Okay, the force that the Earth exerts on the tennis ball. Okay, object A on object B. The force the Earth exerts on the tennis ball is equal in magnitude but opposite in direction. Magnitude is the number, how big the force is. The direction is which way. So the Earth is pulling the tennis ball down. That's the force that the Earth is exerting on the tennis ball. Okay? And I cut myself off here to the force that object B exerts on object A. So if A is the Earth, B is the tennis ball. Okay? The Earth, object A, is exerting a downward force on the tennis ball, is pulling the tennis ball down. Newton's third law says that the tennis ball is pulling up on the Earth just as hard as the Earth is pulling down on the tennis ball. Okay, and this is true for every force. Okay, if I walk past someone in the hall and I shove them, okay, and they go flying across the hall, or wobble, whichever happens, okay, the force that I exerted on their shoulder is equal in magnitude, but opposite in direction to the force that their shoulder exerted on me. When I pushed them, they pushed back with an equal force. The size of the force applied was the same. Well, why do they move and I not? Well, probably because they were surprised. I was braced. I was prepared to shove them. They were not necessarily expecting it, and so they move more easily. Why does the tennis ball fall and the Earth not rise? Same thing, except a slightly different. The mass of the Earth is literally astronomically high compared to the mass of the tennis ball. So while they experience the same force, they do not experience the same acceleration. The acceleration of the Earth is infinitesimally small compared to the acceleration that the tennis ball experiences because of Newton's second law. So the tennis ball moves and the Earth doesn't. In reality, yes, it moves just a itty bitty tiny bit, but we can't tell from here because the Earth is massive compared to the tennis ball. This is true every time you jump, every time you throw something up in the air. It is pulling up on the Earth just as hard as the Earth is pulling down on it. Okay, now, for paraphrasing this, Another way to say this might be, and you can kind of phrase this, however, but you need to write a paraphrase. Actually, I'm not going to give you one. I want you to write down a paraphrase of this based on the explanation that I just gave. Paraphrase B here, down here, and write something out. Pause this and do that when you're done with that. I'm going to go ahead and scroll down to the law of gravity, and we'll talk about that one. All right, I'm moving on. So, Newton's fourth law is the law of gravity. Now, gravity is a deep, dark subject that we're not going to get into much in this class. Honestly, even my physics class doesn't get too much into this because Newton said, hey, gravity, here's how it works. And then Einstein, this other physicist you might have heard of, came along and said, yeah, actually, gravity doesn't exist. It's how we perceive the curvature of space-time, which is a whole other conversation. So we're not going to do too much with gravity. We will do a little bit with it. Mainly, I want you to know these two equations. But first, the law. Okay, the force of gravity is directly proportional to the product of the masses and inversely proportional to the distance that separates them. And there is one more thing that I'm going to add real quick. So you're going to have to add this manually on your paper. One sec. All right. So first off, the actual premise of the law is that every object that has mass exerts a gravitational force on every other object that also has mass. Okay, I am standing here right now looking at my chairs sitting on top of the table over here. The chairs are exerting a gravitational force on every other object in the room. The table is exerting a gravitational force on every other object in the room. It's pulling it towards it. But why don't we see? Why doesn't everything just clump together in a giant wad of crap that crushes all of the living things around it? Why doesn't that happen if this is true? Well, it's because of that second thing that I already said. That force, that gravitational force that every object experiences is directly proportional, or goes up as, the mass of the objects involved. So the two chairs have a very small mass, so they exert a very small gravitational force on each other, and inversely proportional to the distance that separates them. Farther apart they are, the weaker this force gets. There is a force, and in some cases, we can actually measure it. But it's so weak that we don't really see it unless it's something the size of a planet or a moon. We can't really perceive that gravity. Some asteroids are large enough that we can perceive the gravitational force. Like I think it was asteroid Bennu that we recently, 2 or 3 years ago, we landed a probe on, and there was enough gravity on the asteroid that the probe didn't just float away. It stayed there. But yeah, so there is that gravitational force. All objects have gravity. It's not just the big stuff, but the big stuff is the only stuff that has a large enough force that we notice it. Okay, now this is Newton's gravitational law. It is an equation. Okay, it says that the big G times big M times little m divided by r squared is equal to the gravitational force. Now, Newton's gravitational force is also known as the absolute gravity. This is true for any two objects. You can calculate the gravitational force that exists between any two objects with this. Okay, but this equation is also customized just a little bit to work for space objects and satellites. Okay, like the moon. The moon is a natural satellite. Earth is a satellite of the sun. Okay, so gravitational force that exists between any two objects, or the absolute gravity, that's what the Fg is. Okay, big G, this letter in the equation, is the universal gravitational constant. Okay, it is a number that is the same everywhere. For all objects of mass, this gravitational constant stays the same. Okay, and which has its implications. if you're interested, at the end of the video, I'm going to talk about the 28 universal constants just a little bit. Big M is the mass of the central body, or the mass of the larger object. Okay, this is the mass of the thing that is being orbited. So if we're talking about the moon and the Earth, okay, then Earth is big M. Okay, if we're talking about Earth and the sun, then the sun is big M. Okay, little m is the mass of the satellite, or the mass of the smaller object. So for Earth and the moon, little m is the mass of the moon. For Earth and the sun, little m would be the mass of the Earth, because the Earth is significantly smaller than the sun. Moon isn't that much smaller than Earth, but the Earth is way smaller than the sun is. And then r is the distance between those two objects, how far apart they are. Okay, and that is squared, you will notice, meaning that the distance separating them has a much larger effect than the masses does. The farther apart you move something, this gravitational force goes down fast. Okay, gravity decreases rapidly as two things move apart. Okay, you need to know what all these variables stand for. Okay, then we have the simplified gravity equation, which is where all of our actual calculations for this unit are going to be. Yes, you will have to do some conversion tables in this unit. We'll get to those later, though. That's the last topic for the unit, will be the calculations. Okay, so this is F little g equals little m little g. This is local gravity. Okay, it's the gravity of, the gravity, can't read backwards again. Gravity near, good Lord, couldn't read that word. Near the surface of the Earth, also known as local gravity. Every planet has its own local gravity. Every planet has its own little g. Little g is the thing that changes here. Okay, so little g is the gravitational constant for whatever the object is. In the case of, for us, it's going to be the gravitation near the surface of the Earth. Okay, or you could say it's the acceleration caused by gravity near the surface of the Earth. Okay, and that value is a number. It is not actually 10, but we are going to use 10 in this class because 10 is a really, really convenient number. You can do a lot of really easy math with 10. So we're going to use 10. Okay, it's actually 10.0 because we want to have 3 sig figs, but yeah, we're going to use 10 because, yay, math is easy when you're using tens. And then the last m, the little m, is actually the same thing as it was up here. It's the mass of the object near the surface of the Earth, or the mass of the smaller object. Okay, so the thing interacting with Earth. So for me, I am the thing the Earth is interacting with. This force that the Earth is exerting on me is my weight. My weight, 180 pounds. Okay, by the way, Fg is measured in newtons, not pounds. That's the conversion thing we'll be doing later. So we could calculate my mass using this equation. We could calculate my mass in kilograms, which is basically what we'll be doing later. Also going the other way. I give you the mass, you figure out how many pounds it is. Okay, now that's pretty much it. That's the end of this video topic. I'm going to go back and talk a little bit about constants, but in practice for your quiz over all of this, that quiz is, or there is a worksheet, 8.1a, that is kind of an overview worksheet where it's got just a little bit of everything in it. There will be special worksheets, or separate worksheets linked as well that will cover all of these. Your first assignment after we finish the lecture, or your first assignment if you are not at school today, is to do worksheet 8.1a. Okay, that's the worksheet where you have all of this laid out in relatively simple manner. It's kind of a brief overview of everything. That's your assignment for today. Now, I want to go back a little bit and talk some about this. Okay, so there are 28 what we call cosmological or universal constants. Okay, they are exactly the same everywhere in the universe so far as we can tell. Everywhere that we've been able to observe, these 28 values hold true. The gravitational constant is 6.67 times 10 to the negative 11th. It's incredibly small. There is also a Coulombic constant, which is electrical force. There is I'm blanking on it. It's not Tesla. There's a magnetic force constant as well, but I don't remember what it's called. Okay, there are dozens of these, 2 dozen, in fact, or a little more than that. Okay, and every single one of them is perfect. It's exactly where it needs to be. If it was just a little higher or a little lower, things wouldn't work. Life wouldn't work. Okay, so there are 28 values that physics has given us that we have been able to prove that these are constant everywhere. And if you imagine a ruler that is the length of the Milky Way galaxy, okay, and there's a little slider on there that you can move back and forth for the gravitational constant. Okay, if you take that slider and you move it just a little bit higher, so the gravitational constant is just a little higher, then all of a sudden the entire galaxy collapses into a black hole. Just a tiny, tiny adjustment on this massive scale will completely obliterate the entire galaxy. If you move it just a little bit the other way, then hydrogen can't form. Protons and neutrons and all of these things like planets and stars, there's not enough strength to the gravity for all of these things to form. Okay? The gravitational constant is perfect. If we move it just a little bit in any direction, then gravity is either way too strong or way too weak. And there are 28 values like this that we found in physics. And it might be more. This is what it was when I was in college, which was 15 years ago. 12 years ago. 12 years ago. 15 years ago when I learned about this. So yeah, I wanted to leave off with that. That's where I'm going to stop. Have a wonderful day, evening, night, morning, whatever. And I will see you next time.